Operations for Rainer Equipment Systems, an Etnire International company. This will be my 13th ISSA. It's been a pleasure working with the team that worked diligently to put this program on. It's a very valuable tool. Hopefully you'll walk away from this class with some gained knowledge and appreciation for your time investment. Let's get started. What we're going to cover today. We're going to talk about equipment history. It's valuable to understand where we've come from, where we're at, and maybe an insight into some of the cool things that are coming down our path in the future. Why do we calibrate? It's a really important question. There are folks out there that don't appreciate the value of calibration. And if you don't understand the details and all of that, it's hard to look at it and say, well, that's a good investment of our time. But it really is a valuable process, and we're going to talk about the details. What is the mix design? The mix design is your formula. As we're making changes to the machine, we're making changes to the mix in the field, the temperatures change, the environmental conditions change, there's things that happen. The mix design really helps us understand where the parameters are, what we can work with, and we'll talk about that in pretty good detail. How do we calibrate? We're going to talk about the mechanics of the process. You get a glimpse into some of the details. There are different machine manufacturers that have very different ways to go about it, but this is a pretty standard process we'll address from a generic perspective. When do we calibrate? This again is another valuable question that as a company owner, as a inspector, you really understand and appreciate when we need to do this. What is bulking? We've got a fun demonstration to show you what bulking is and how it can affect us. It's a real kind of an eye-opener seeing the live demonstration. And then we're going to talk about field applications. Our first side today on equipment history is a pretty good flashback to some rougher times. You see that the machine on the far right hand side, very environmentally friendly machine, 1 horsepower, far under our EPA guidelines today, be a pretty attractive machine, doing some type of scrub seal. On the other side you see some gentlemen out working hard doing what I can only guess to be crack sealing. So the 1950s, cement mixers were used and discharged into a spreader box similar to the type of spreader box that we use today. So here we have a young SB804. Now this is a newer version, but in the 1950s and 60s, Frank Young built the first machine designed for this purpose for making slurry. The SB804 rapidly became the most popular machine in the country. It had an air-cooled Wisconsin engine, chain drives, and dry clutches to engage the jack shaft and or pug mill. A spiral type pug mill, mixing pug mill with manual diverter control, and a manual wheel control to open and close the delivery gate. The picture here shows an upgraded SB804A that had some fairly advanced controls for its time. In the 1970s, Mitchell came out with a larger model machine. They adapted a hydraulic motor for open and closing of the gate, had larger diesel engines, they had a single shaft paddle type pug mill, and they had liquid additive systems. The advancements in the material had grown, machines were adapting and growing along with them. Creative thinking and field experience brought about these changes. Moving on. In the 1980s and 90s, advancements in hydraulic systems brought many changes and upgrades to the slurry market. Chain drives and dry clutches were gradually replaced with engineered hydraulic systems. Conveyor systems were re-engineered and upgraded to hydraulic with sensors to automatically shut down if the machine had belt slippage. Belts were designed to last for years. Pug mills were engineered with twin shafts and hydraulic drives. Spreader boxes were improved and strengthened. Digital counters began to appear to monitor various systems. In the picture here, you can see the digital displays above the operator's head. Good collection of gauges to monitoring the machine. Machine quality took an overall large step forwards. Creative thinking and field experience brought about these changes. Now we're getting to modern day. From 2000 through today, our industry has benefited from significant improvements in technology advancements. We've seen continuous improvements with joystick controls, manual and Hall effect designs. Hall effect joysticks have no mechanical components. They are moving and using magnets to measure the position of the joystick, so they last longer and the accuracies stay much higher. You've got onboard program logic controls. Allows us to manipulate the machine to work within from a computer controlled and make it much easier for the operator. You got IP67 displays. It means we can have high pressure washdowns. We can have the electronics on the machine that will hold up in the harsh environment that we as Slurry and microsurfacing folks live in. The control and monitoring systems of various types of advanced. We've got LED lights, load sensing hydraulic systems. Load sensing is a process where we can reduce the power demand on the either the truck or the truck's engine or a side engine, depends on the machine that you have, and manage the pressure load on the systems. Very helpful in today's modern machinery. Control area networks. Control area networks have simplified the wiring systems. Instead of very large wiring bundles, when problems occur, and they will, that it's much simpler to diagnose, much simpler to get to the solution and get the machine back up and running. In the coming years, you're going to see many more improvements as machine manufacturers, such as ourselves and the other sponsors of this ISSA workshop, push the boundaries and search for better performing machinery. Now we get to talk about why. The why do we calibrate? It's an investment of time and money. It's important to understand the reasons why we put that investment into our company, into our systems. For slurry, the recommended performance guideline for emulsified asphalt slurry seal is A105. This is a standard, an ISSA standard. There may be a version newer than the one I've listed here, but this is what we've got. And then there's a similar one for microsurfacing, and that's the A143. Again, talking about the why we calibrate. So calibration, each mixing unit is used in the performance of the work shall be calibrated in the presence of an inspector prior to the start of the project. Previous calibration documents covering the exact materials to be used may be acceptable, providing the calibration was performed during the previous 60 days. The documentation shall include an individual calibration of each material at various settings, which can be related to the machine's metering devices. Any equipment replaced affecting material proportioning requires that the machine be calibrated. No machine shall be allowed to work on the project until the calibration has been accepted. ISSA Inspector's Manual describes a method of machine calibration. ISSA contractors and/or machine manufacturers may also provide methods of machine calibration. As a machine manufacturer, it's very important that we know exactly what's going on. If we make a change to the machine, a key component is changed for some reason, that can affect the output. The calibration lets us know what our volumes are. And if something changes, is it a mechanical issue? Is it a chemical issue? What's going on? Calibration lets us understand what that is. And we'll refer again to the A105 or the A143 if we have questions on the performance of the material. Now we talk about kind of the chemical side. Quality can only be achieved if you have a process in place and a means to measure the results. The operator needs to know how much of each ingredient is being added into the mix. We are making the material. We're not going to a plant and getting a pre-made material that's been mixed in a controlled plant. We're doing it on the streets, on the parking lots, on the highways. We're doing it in the field, so we need to know what's going on so the material will perform as expected. Aside from the obvious chemistry concerns, there's another very important reason for calibrating our machinery. Companies get paid on the volume of materials used, and agencies pay on the volume of materials used. Calibration is the process we undertake to learn and document the exact volume of material each machine function produces in a given condition. We have to measure the gate so that we know how much aggregate is passing through a given size, given space. We have a material pump that is pumping the emulsified asphalt into our mix, and that too needs to be calibrated so we know the exact volume that's being added. Slurry and microsurfacing mix designs formulations are based on dry weight of aggregate. So the aggregate is the base of all the formulations, all the math. The weight of an emulsion oil, the weight of water, the weight of additive, and the weight of cement. Setting the machine to a given mix design and producing a consistent material requires accurate information. So it's so important that we do a calibration so we know exactly what is going into our mix. We want the material we put on the road surface to last and perform as well, if not better, than expected. Let's talk about what is a mix design and why do we need one. All right, we've got a sample mix design. This is a doctored up version of a real life mix design. Our laboratory for this example is the ISSA test laboratory at Texas Station. The list of project, this is the 2021 ISSA workshop. It tells us what the mix design is. It tells us where it came from. It tells us that the emulsion is a ISSA LMCQS1H. A little bit farther down, it talks about the mix design for this aggregate. Emulsion is as follows. It says the percentages are based upon the aggregate. So that's 100%. Very important to understand and know that the rock is the base of all the formulations and the math when we're calculating. The recommendation is based on ASTM and ISSA test procedures with supplied specifications. They're going to blow it up so it's a little bit easier to see. The specification is on the far right hand side. So we're calling out 100%, we're 100% on the aggregate. On the emulsion, it's giving a 12 to 18% for the spec. The mix design says we can operate within a 13 to 15%, and that's where we can get the performance out of the material. Specification is one thing, the mix design tells us we're within those parameters, but here's where we need to be successful. It shows what the residual asphalt is going to be. Again, we're talking an emulsion, so it's a water-based emulsion, and that water is going to be pushed out of the mix. Our residual asphalt, the spec calls for 7.8 to 11.7. Our mix design says we are going to be within 8.5 to 9.8. So we're well within the specifications. There's not a spec for water, aluminum sulfate, or cement. In some places you don't use aluminum sulfate, you'll use a different set control additive. But here we're talking water, we've got 8 to 10%. We need to have enough water in the system to be able to move the material. Its purpose is to help us get the material where we want it to be and spread evenly on the surface. We want the least amount as possible, but enough to do the work. Too much water, and we can float the asphalt out of the material. We can cause horrible damage to the material, and we'll end up having material asphalt running into the gutters, running off the road. We've got a real problem if we exceed those limits. Aluminum sulfate says you don't need any, or you could use as much as 0.5%. Cement says 0.5 to 2 will give us a good performance. And the asphalt and the emulsion here is 65%. So it's important to understand the mixing or the testing protocol. So how do they come up with the mix design? What do they do in the laboratory to get the results? This is all explained typically on the mix design. It says obviously they're adhering to the ISSA Technical Bulletin 106 and the Technical Bulletin 115. The trial mix time was at 80 degrees Fahrenheit, and it was for over 2 minutes using a 13.5% emulsion, 9.5% water, and 0.5% aluminum sulfate. The consistency test will be found in Table 1. It shows down below what the mix percentages are. And it says the consistency test, the surface was not tacky, so it passes. The split consistency test says uniform. There was no aggregate migration. The aggregate broke when the sample snapped, indicating good adhesion. And then the wet stripping says it was past 100%. There were no uncoated particles. The wet track abrasion test, that's the ISSA Technical Bulletin 100, with a 1 hour wet track abrasion test, the results are found in the table listed here in Figure 2. It says the test is used to determine the minimum amount of asphalt needed. This material has excellent results. The samples were broken in half after the wet track abrasion and inspected. There was no evidence of migration. The rocks broke when the samples were split, indicating the good adhesion of the emulsion residue to the aggregate. All laboratory testing that helps us understand what's supposed to be happening. Now, this is in a laboratory with controlled temperatures, controlled environment. It can be very different in the field. When we have good calibrations, we understand the mix design. When we run into difficulties, it really helps us get to an answer and a solution much faster. This can be a little dry, so I won't spend much time here. I'm just going to run through it real quickly, just noting what the test is, what the technical bulletins are that detail what the test is, and it gives you the results and what the requirements are. So you can dig into this in greater detail to understand it, but this is included in many of the mix designs. The aggregate data, so this is what we talked about for Table 2. This tells you what the percentage of different size particles are in the mix of material. The ISSA spec details that there has to be a certain amount of particles, different size particles, in the material. Unlike a chip seal, which is a single size particle, these systems need to have the different size particles because we are a thin surface treatment that's applied, and it's got to have the strength to hold together. And the different size particles allow us to do that and have a very strong material. Just quickly, I'll just show on the left-hand side, you'll see that the gradation sieve. These are the sizes of the screens that the sample material is put into. There's a shaker that will shake the material and help allow the material to pass through these different screens. And we measure how much of the different particles were retained in the different sieves. And we've got a type 1, a type 2, and type 3. Type 1 is quarter, type 2 is I'm sorry, type 1 is an eighth, excuse me, type 2 is a quarter, and type 3 is 3/8. Now we get to talk about how do we calibrate, the process itself. In the picture shown here, you'll see that the machine is loaded, the material is being laid into windrows. Why do we do that? Because the rock is valuable. We don't want to waste it. We're going to run the material out in hopefully a place that we can easily reclaim the material and have the least amount of waste possible. Do a quick run through here talking about what are the components on a slurry microsurfacing machine. How do we where the raw ingredients kept and how do we get out of there? So just quickly, number one's aggregate hopper. That's where the raw aggregate is kept. 2 is our fines feeder. That's where our cement or our hydrated lime would be kept. That would be that's added into the mix. 3 is the gate. The gate is what meters the amount of rock that is allowed to pass with 1 revolution of the head pulley. We'll talk about that in the next slide. 4 is the conveyor. That's what pulls the material out of the machine, out of the hopper, and allows it to and dumps it into the pug mill. 4 is where the emulsion is injected in. 6 is the water injected into the mix. You notice that's happening in a very small space. The mixer, which is the pug mill, number 7, that is designed to take all of these raw ingredients and blend them. We're not beating them, we're blending them nicely into homogeneous material. 8 is that final material that's been mixed thoroughly and is now discharged from the machine. And 9 is the box. The box is what rides along the asphalt surface and sets our mat thickness and gives us the final look to the material. All right, this is a little cartoon to kind of show how the process works for the head pulley. This is a 10 counts. We've got a 3-inch gate setting, so let's just run this through. So we're going to open the gate to our 3-inch gate setting. We're going to start the conveyor, and we're going to run for 10 revolutions of the head pulley. So we're doing calibrations. That's what we're measuring, is head pulley revolutions. And we're measuring how much aggregate is allowed to pass through that 3-inch gate setting over a given amount of revolutions. So here we've got 10 counts, 3-inch gate setting, and now we measure we weigh the vehicle and figure out how much material did we discharge out of the machine. So we have to start with loading aggregate into the machine. So we're going to start with a full hopper. We don't want to have a partial. We want to be able to be as sufficient with our time as possible. With a loader like this, it's pretty easy to fill the machine very rapidly. So we want to fill the machine up. So I added the note in here regarding the moisture content of aggregate. Okay, so to determine the moisture content, we need to determine the moisture content of the aggregate. So we're loading this from a stockpile, from a pile of aggregate that's been sitting out here. And in the picture before, this is outside. It's been subject to inclement weather. We've got moisture. We need to know what that is. We'll discuss this in greater detail when we get to the bulking section of the presentation. Okay, here we show a very typical machine design with an adjustable sand gate. So we are looking at the backside of the aggregate hopper, and this is the gate that we talked about a few minutes ago, where we increase or decrease this gate setting to control the amount of aggregate that passes through. Here we see the operator adjusting the gate height. The higher the gate, the more aggregate that we get through. The more aggregate means that the lower the oil content, because we're getting more rock. The oil content on this machine is a consistent design. So the oil stays constant, the gate for the aggregate changes. So the lower the gate, less oil, the less rock, the higher the oil content. There are machine designs out there that kind of do the opposite way. They'll have a fixed gate and they'll control the emulsion content. But this design here is a very typical design that's been in the industry for a long time. While we're looking at this, we talked before about the way where the materials come in. You'll see the blue bar with the gold spray tips on there. That's where the water is being injected into the mix. And the silver bar with the gray T's on there, that is where the additive, the liquid additive is being added in. The black tube is where the Portland cement is coming in. And just below this picture you can't see is where the emulsion is added to the mix. So it's all these raw ingredients are added in a very, very short space. Here's a close-up view of the gate. Kind of hard to see, but a little area of aggregate's been cleared out of the way, so that could be they could measure directly to the conveyor belt. It's important to do this adjustment with aggregate on the belt because the belt will flex. Right now with the weight on it, it is at its lowest setting, which is where you're going to be operating. If we talk about this guy here, this is the water I mentioned before, and down below is the additive, the liquid additive that's added in, and then this here is where we're adding the Portland cement comes into the mix. Here's a little bit better view. We can see that the sand gate height is being set. We've got a tape measure and we've cleared out a spot so we can get a good flat surface. We don't have any obstruction in the way, and we can get a very tight number on where the gate is set. Again, these are all mechanical parts that can move. It's the same thing why we would calibrate if the emulsion pump were changed, because small differences can make a big change. So we want to make sure that we've got this adjusted right. Coming back to the statement before, lower oil, or the lower, more oil, higher, less oil. All right, so now we've got our machine filled full of aggregate. We've got our gate adjusted to where we're going to do our calibration settings. So now we need to take the truck and we need to run across the scales and we need to get a full machine weight. All right, we've got our calibration sheet. So we're going to record the information. So what we did, we filled our hopper with aggregate, we adjusted our gate setting, we went to the scale and we got our full weight setting. We need to record that exact number. We're going to put that in here. So we started at 65,260 pounds. Okay. Now, on our aggregates, we talked before about the pug mill. It is very, very important to keep in mind the pug mill is a dangerous device that will eat you if you're not careful. Okay? So we never want to operate the machine with the pug mill uncovered. Too risky. Be safe. Okay? All right, now we can actually start our calibration. So some of the newer machines have an automatic operation that makes this process much simpler. If your machine is equipped with this, you can just simply enter in the number of counts and press start. And the machine will stop automatically when you hit that desired number. If your machine is not equipped with this, no matter, continue to operate the conveyor as you normally would. Make sure you're keeping very good track of the counts. Get as accurate to, as close to your set point number as possible. If you're over a count or two, it's not a big deal. Just make sure you enter in the correct number of counts, the actual number of counts that you ran on your calibration sheet, because that will affect the calibration numbers. This last thing just says the conveyor will automatically stop when you get the desired number of counts. That's pretty handy. So we've got the pug mill running. We've started the machine. We're the conveyor system. We're running the aggregate through. We're going to lay the material in windrows. Again, we want to recapture this aggregate, so we want to keep it as condensed and tight as possible. We do have to move the machine forwards, because if you don't, you will end up dry plugging the pug mill, and that's no fun. So we preset the sand conveyor speed approximately 30% lower than normal operation, because we are running a dry aggregate through the machine, and it will not flow near as well as our emulsion will. We start the sand conveyor and adjust the pug mill speed if necessary. You can increase the pug mill speed to help push the material out the machine. I will just say that you want to make sure in operation that you're not running the pug mill speed too fast, because we want to blend the material, not beat it into submission. So this is an important note to keep in mind. And remember, this is good aggregate. It has value. It's a cost. We want to keep it in a location where we can reuse the material as much as possible. Okay, we ran our number of desired counts. We stopped the machine. We let the pug mill continue to run to push out any remaining aggregates that were in the pug mill. So we've got all the material that has been discharged from the head pulley out of the machine. So all that weight is gone. We go back to the scale and we weigh the machine. Our weight here, our empty weight, was 59,540 pounds. So in calibrating the aggregate, we want to run a series of 3 calibrations at each gate setting. If all 3 calibration cycles net similar results, continue to the next gate setting. If one is off and the other 2 are the same or similar, you can run a 4th to determine if an error occurred or if a greater problem is present. Common thing would be the driver was not lined up on the scale correctly, and and just got an odd reading. Those types of things happen. I will say that when you're doing the calibration, you should use the same driver in the same truck. Don't switch drivers, because we weigh different weights. Don't let them, they're not going to go and load the truck up with fuel in between. When they have a full weight between full weight and empty weight, we want that to be only weight difference on the machine is what materials we have offloaded. So it's just an important note to make. All right, in this series, or in this page, we've run our series of 3 at a 3-inch gate setting, and we had 59,540. We did 100 counts, so the 5720 is the weight difference, divided by 100 counts is 57.2 pounds per head pulley revolution. That was on our first cycle. Our second cycle, obviously our empty weight is our new full weight. We ran our calibration. Our empty weight was 53,820, and our net difference was 5720. How convenient. We did 100 revolutions, so we are at 57.2 pounds per head pulley revolution. On our third cycle, because we're at a 3-inch gate setting, we're able to get away with running all 3 with the 1 load. So our empty weight on 2 is our full weight for 3. Our empty weight came out at 48,120. This one, we were at 5,700 pounds. At 100 revolutions gives us 57 pounds per head pulley revolution. An important thing to note is that most scales have a 20-pound swing. They're pretty accurate, but they're weighing a very heavy equipment. So it can have a 20-pound swing either direction. That's why the higher number of counts you do, the greater your accuracy is going to be. So this weight difference here could strictly be just a weight swing at the on the scale. So our average of those three, so we add those together, divide by 3, is 57.13. And now we've determined that we had a 2% moisture factor. So we've got a 0.98 moisture factor. So our dry aggregate weight would be 55.99. It's important to understand that, and we'll get into greater detail farther in the presentation. Okay, we have just completed our 3-inch gate setting evolutions, and now we're going to go on to our next gate setting. So we're going to go to our 4-inch gate setting. We're going to duplicate the process. Again, loaded machine, got the weight, the aggregate weight on the belt. We're measuring from the belt surface to the bottom of the gate, so we have a very good accuracy with the same measurement device. So our consistency is there. And we're going to repeat a third time at a 5-inch gate setting. So we'll repeat this process again. So we have a 3, a 4, and a 5-inch gate setting, and we're doing 3 cycles of each one. So there's, we talked before about the cost of calibration. There's a lot of time invested into doing this, so it's important to do it well, to do it right, and to understand why we're doing it. Okay. I mentioned before